In this last segment of Chapter 2, we're going to explore the concept of risk pooling as a strategy for dealing with uncertainty in the demand for the products that have to flow through the supply chain. Now, what happened is that if you have several items, or if you have, say, for example, multiple distribution centers, it is possible to mitigate against the variability in demand by actually combining those distribution centers into a single distribution center. So there's some advantages to be gained, because what you're doing is you're really aggregating the variability, and when you aggregate the variability, you actually reduce its net effect. So demand variability is reduced if one aggregates demand across locations. So for example, if we're thinking about the demand for a product in Sydney, Yarmouth, and say Halifax, if you combine the three demand streams or the three demand patterns, what you will find is you'll get less variability by aggregating them into a single demand. And the reason for that is because the highs and lows of one location might very well offset the highs and lows of another location. In fact, this the benefit of aggregation tends to work well when you have the variability in the different locations being actually more or less negatively correlated. All right. So that means if one goes up in one location, it goes down in the other. When you combine them, they kind of even out each other. So more likely that high demand from one customer will be offset by low demand from another. And the reduction in variability allows for a decrease in safety stock. Because if you remember the safety stock formula, which often has a Z value associated with the service level, the standard deviation of the demand during the lead time multiplied by the square root of the lead time, what happened is that if you could reduce sigma, which is the variability of the demand during the lead time, then you obviously will need less safety stock. Excuse me. So we use standard deviation measures so that we get a sense of the variability of the demand pattern. And then coefficient of variation, you may remember from statistics, which is another measure, allows us to express the standard deviation as a fraction of the average demand. And those measures are useful to give us a sense of the variability, or relative variability, particularly if you're comparing different product types. So let's take a look at a case that will sort of demonstrate to us the benefit of risk pooling by bringing together the demands or the forecast from multiple locations and aggregating them into a centralized distribution center. So consider a case where we have two warehouses for distribution, one in New York and one in New Jersey, and we've partitioned the market into sort of like into two regions. And so that means the customers will receive their goods from the warehouse or the distribution center that is closest to them. All right. The warehouses receive the materials from another location, let's just say Chicago. Chicago could be where the manufacturing plant is. And that they each want to have a service level of 97%, which means that there's only a 3% chance of stock running out of stock. So instead of having the multiple products in the New York location and the multiple same products in the New Jersey location being treated separately, what if we replace that with a single distribution center? And of course, we would have to find the right location for that single center, and see what happens if we aggregate the demand into the single center. So what may happen is that you may actually get a little slight increase in the lead times, because depending on where that facility is located. However, the total investment in inventory could be reduced. And so if you look at some historical data for, we have two products, A and B, at both locations, New Jersey and Massachusetts, then we would see they have their own independent demand streams. So here we go, we see the demand stream for product A in Massachusetts, product A in New Jersey, and so forth. We could take each of those and compute for them was the average demand at that location, the standard deviation of the demand for that location, and the coefficient of variation. Remember, the coefficient of variation is when you express the standard deviation as a fraction of the mean, and you get those values. So when you explore that, we would see the relative variation. We see product B has quite a bit of variation in both locations, right? That relative to the mean, that is. So from that, we could actually calculate what we call the average demand during the lead time, which is usually the lead time times the average demand. That gives you the average demand during the entire lead time. And the safety stock is calculated from the formula Z, which has to do with the service level, multiplied by the standard deviation of the demand, multiplied by the square root of the lead time. So we could actually calculate the safety stock. And remember, safety stock is just the sum of the average demand during the lead time plus the safety stock. And that gives us our reorder point. So we've calculated reorder points for item A at Massachusetts and item B Massachusetts, item A Massachusetts, and so on. So they look relatively close, 65, 62, 4, and 5, and so on. However, when we combine them, we will see that that we get a little bit of a benefit. Look at the reorder points now. So you have 65 and 62, which gives us approximately 127. But when you put them together, you could actually reduce your reorder point down to 18. And instead of 5 and 4 give you 9 items in stock, we would only need 6 if we combine them at that particular location. All right. So we certainly see some potential benefits in this regard. All right. So there's some savings in inventory, and the calculations actually are not. I think that there might be a couple of errors in the calculations. However, I think just to get a general sense that if we look at the savings, it seems to make sense. Well, just in the sense that we expect savings, but I believe that there might be 1 or 2 errors in the calculations that I'll have to check out. Anyway, in the New Jersey warehouse, we see for product A, the average inventory is about 88 units. Now, how do we determine the average inventory? The average inventory is the order quantity, the average of the order quantity. So Q over 2 plus the safety stock. So think about it. Safety stock is what you carry all the time, but the order quantity Q has to be depleted over the inventory cycle. So Q is what you start off with. At the end of the cycle, you should have 0. So 0 plus Q over 2 will give you the average inventory that relates to the order quantity. But then you keep this amount in stock all the time. So in the long run, you'll have that amount, which is your safety stock, plus Q over 2. If you use that formula for the, and you apply it to the data here, so the if you were to take Q over 2 plus the safety stock, that's how you should actually get the values that we are looking at on the next page. So for example, 132 over 2, which will give you approximately 66, I believe that is 66, and if you add that to your safety stock, 66, well, that should give you approximately 91, right? So we see here in Massachusetts, you have the average inventory for product A is 91 units, but it doesn't compute for New Jersey. So I believe that there might be an error in the calculation. Anyway, as you could see, if you look at for product A, you would have to have 88 plus 91 units, but when you compare that in the centralized warehouse, you would only need 132 units, and that gives us a major savings. If you look at product B, at the 2 warehouses, you would have in New Jersey an average of 15 units and 14 units, which gives you 29, but when you centralize them, you get down to 20 units. And so therefore, it's a way of trying to reduce inventory by pooling the risk associated with the uncertainty in the demand. And when you do that, not only do you lower the variability, but because you lower the variability, you're now able to keep less inventory in stock, which makes sense. So the higher the coefficient of variation, the greater the benefit from risk pooling. In other words, if there's very little variability in the demand for the products, what's the point of bringing them together? So the more you have variability, the greater your opportunities for risk pooling. All right. The benefit from risk pooling depends on the behavior of the demand from one market relative to the demand from the other, and the benefits tend to be higher if the variations tend to be negatively correlated, or the demands tend to be negatively correlated. Reallocation of items from one market to another easily accomplished in centralized systems, right? So, for example, if you had a two distribution centers, you might decide to close one and then move all the products to another. So you could actually achieve some of the benefits from risk pooling that way. Centralized versus decentralized systems. Well, what are some of the things that we would observe? One is that centralization tend to lead to lower safety stock levels. Because you need lower safety stock levels, higher service levels for the same inventory investment is centralization. So technically, you need lower safety stock levels for the same level of service compared to the centralized system. But if you kept the same amount of inventory that you would normally keep in a decentralized system, in a centralized system, then obviously you should get greater service levels from that. So the service level will be higher for the same level of inventory investment. Overhead costs higher in decentralized systems, of course, because you have repetition. The customer lead times tend to be lower, however, in a decentralized system. Why? Because you tend to move, if you decentralize the distribution network, then you would move the distribution centers closer to the customers. But if you do some centralization, you have to find that midpoint. And so therefore, you could find a location that actually increases the sort of transportation costs or the lead times. It could have that effect. All right. So it's not always clear how the transportation costs are affected. Maybe your inbound costs might actually be, the centralized facility could be a little closer to both of the markets, but then now you move further away from the manufacturing facility. So your inbound costs could increase while your outbound costs could decrease, or vice versa. Or both of them can be increased. All right. So I think it's not always clear ahead of time how the benefits actually materialize in that regard. The last concept is something called multi-echelon systems, and eventually, so when you look at an entire supply chain, how much the manufacturer respond in terms of their reorder points and their safety stock levels, given that they have to supply a wholesaler, and the wholesaler must supply a distributor, the distributor must supply a retailer. So we often talk about the echelon inventory, which is basically the inventory at a particular stage in the supply chain. That means we're looking down the chain at a particular stage and we're saying, well, what is the echelon inventory? And the inventory at that stage is basically to take into consideration what inventory is in that facility plus all the inventory that is following that. So if you are the distributor, you must consider the distributor's inventory plus the inventory of the retailers. If you go back to the wholesaler, then the echelon inventory is the inventory of the wholesaler plus the inventory of the distributors plus the inventory of the retailers, and so on. If you go back to the manufacturer, then basically you have the echelon inventory at that stage is all of the inventory in the supply chain, because it includes the manufacturer's inventory plus the inventory all of the downstream facilities. All right, so managing that again, of course, this adds some complexity. And at each stage, one would want to know, well, what should my reorder point be at the manufacturing level? Or what should it be at the warehouse level or at the distribution center level, etc.? And there's some formulas for that. So if you look at this diagram, it shows us very quickly. The retailer's inventory would be their echelon inventory, but the distributor's echelon inventory would incorporate the distributor and the retailer And then if you have a supplier like a manufacturer, then echelon inventory would include all three facilities here. So how do we do our reorder point calculations? If you remember, the basic formula for reorder point is the excuse me, the expected demand during the lead time and the plus the safety stock. So how do we calculate the expected demand during the lead time for a particular stage or particular echelon in the supply chain? And the big difference really is this term you see here, LE. LE. So basically the lead time, an echelon lead time is what we need to calculate, and the echelon lead time is really just the sum of the all of the lead times from that stage. So if you had a distributor level, and there's just between the distributor and the customer and the retailer, sorry, then the lead time is just that lead time between those two. But the echelon lead time for a wholesaler who has to supply a distributor and then who then supplies a retailers would include the lead time from the wholesaler to the distributor plus the distributor to the retailer and then the retailers to their customers. All right. And so when you're considering your average demand, during that echelon lead time, you must consider that entire span of time, and the wholesaler would have to consider that in determining when they should actually place an order, because they have to supply all these downstream facilities. And so that's the formula that's given to us here. You just need to know how to calculate that. And so here's a simple example. If we consider average weekly demand to be 45, standard deviation of the demand is 32, and at each stage management is attempting to maintain a 97% service level, which gives us a Z of 1.88. I know you're thinking confidence intervals, but this is not confidence intervals. This is a little different. You have to look at a 97% as a cumulative value. So in the tail there's really 3%, so that would be the Z. If you were trying to find with a confidence interval with 3% in the tail, that would mean a 94% confidence interval. Notice 95 is 1.96. Well, 94, which would be a little lower, would be 1.88. All right. So don't confuse it with the values for confidence intervals. And the lead time between each of the stages is 1 week. So here are some cost and order quantities that we could do our EOQ formulas for each of these locations. And here's how you determine the reorder points at each stage. So for example, at the retailer, if there's a 1 week lead time, the average demand during the lead time is 45 times the lead time. And then of course this part gives us our safety stock, standard deviation times Z times the square root of the lead time. But now if we go to the distributor, they must consider an echelon lead time of 1 week to the retailer and 1 week to the customer. All right. So then that goes up to 2. And then you could see we use 2 here in terms of the square root of the lead time. All right. That's pretty much what it is. So as you go up the chain, you'll notice that the reorder points get higher and higher. And the only way to reduce that essentially is to cut down on the lead times or cut down on the standard deviation or the variability in demand if you could sort of do that. All right. What if you have more than one facility at each stage? Then the whole process is similar, but it's just additive. You just need to consider the inventory at all of the facilities in a given stage. So for example, if a wholesaler has 3 or 4 distributors, then the echelon inventory for that wholesaler would include the inventory at the wholesaler plus all of the inventory at the various distribution centers. You have to include all of them, plus the inventory at all of the retailers. So this can get pretty complex, but the process in terms of analysis is somewhat similar. All right, so here we go. Echelon inventory at the warehouse will include the inventory at the warehouse plus the inventory at all of the retailers. All right. So some practical issues in terms of the management of inventory. got to think about periodic inventory review. So we have to every now and then make sure that we are aware of what's in the warehouse or in the various facilities. We might actually do that continuously with the use of technology now, or we might do it periodically. Tight management of usage rates, lead times, and safety stocks. So you have to manage those effectively, otherwise you increase your costs in the supply chain. Try to reduce the safety stock levels as much as possible, because that's just inventory sitting there, and so that means you have capital tied up. Introduce ways to improve the accuracy of inventory levels through things like cycle counting. Use an ABC approach to actually streamline and to categorize inventory into different levels of importance. A, most important; B, moderately important; C, least important. And then what you do is you pay attention to the inventory according to the levels of importance. Use quantitative approaches where possible, all right? And then have some metrics that you could use. And supply chain do have multiple metrics. One common one is inventory turnover ratio, but you have a paper that I gave you which speaks to the issue of metrics in the supply chain that we'll discuss, all right? Last but not least is the whole idea of forecasting. Because we're trying to manage inventory in the supply chain, forecasting of demand becomes an important issue, practical matter. How can we forecast most effectively? You would have done some forecasting in your operations management courses if you've already done that. And there are many different techniques that we can use: judgmental methods, market surveys, time series models, trend analysis, models that include seasonal patterns, and we see here what we call causal methods. Causal methods are basically when you have one variable that you believe is actually driving the values that you observe in another. And so, for example, temperature causing an increase in the demand for ice cream. If it is hot, people want ice cream, or people drink more water. That would be an example of some sort of causal relationship. Okay, and those techniques will be reviewed briefly. However, there is an expectation that you would have had some exposure to those in a class on operations management. So in summary, on the forecasting techniques, essentially you need to forecast so that you can try to match demand and your supply. Okay, that's the whole reason why forecasts are always wrong. So hence it increases the errors in the system, because if you have errors actually lead to costs which have to be managed. The longer the planning horizon, the less accurate your forecast will be. So if you try to forecast for 2 years, it's likely that it's going to be less accurate than forecasting for 3 months. Aggregation actually improves forecasting. This is much the same way that we use it in risk pooling. When you combine products, the variation actually tends to kind of wash each other out a little bit, and therefore stabilizes the demand pattern and makes it a little easier to do your forecast. All right, find the most technique that's appropriate, and of course you need the most inventory relative or adequate, sorry, or appropriate inventory policy. Okay, so that brings us to the end of that segment on inventory management and risk pooling in the supply chain, and we hope that you found the video summary sort of a useful addition to your chapter reading.